Antoine Lavoisier was a French chemist born on August 26, 1743, in Paris, France. He is considered one of the fathers of modern chemistry for his pioneering work in the development of the theory of combustion and his contributions to the field of quantitative chemistry. Lavoisier was the son of a wealthy Parisian lawyer, and he was well educated from a young age. He attended the Collège des Quatre Nations and later studied law, although he was more interested in science. In 1764, he was admitted to the Academy of Sciences, where he began to study chemistry. In 1772, Lavoisier married Marianne Pierrette Pauls, the daughter of a prominent family who shared his interest in science. She would later become his collaborator and laboratory assistant. Together, they built a laboratory in their home and began conducting experiments. Lavoisier's most significant contribution to chemistry was his discovery that combustion and respiration involve the same process of oxidation. He also showed that air is not an element but a mixture of gases, including oxygen and nitrogen. He named the former oxygen and demonstrated its role in combustion and respiration. Lavoisier's work led to the development of the law of conservation of mass, which states that the total mass of a closed system remains constant over time. He also discovered the role of oxygen in rusting and fermentation, and he showed that water is a compound made up of oxygen and hydrogen. Lavoisier's work in quantitative chemistry was also groundbreaking. He developed a system of measurement for chemical reactions, including the use of a balance to measure the mass of substances before and after a reaction. He also introduced the concept of stoichiometry, which is the study of the relative quantities of reactants and products in chemical reactions. In addition to his work in chemistry, Lavoisier was also involved in economics and politics. He was appointed to the French Academy of Sciences in 1768, and he became a member of the French Academy of Medicine in 1777. He was also a member of the French Academy of Inscriptions and Belles Lettres and was elected to the Royal Society of London in 1769. During the French Revolution, Lavoisier became involved in politics and served as a tax collector. However, his wealth and association with the former royal court made him a target of the revolutionaries. He was arrested in 1793 and tried for treason. Despite protests from his colleagues, including Joseph Louis Lagrange and Pierre-Simon Laplace, Lavoisier was convicted and executed by guillotine on May 8, 1794. Today, Lavoisier is remembered as one of the most important figures in the history of chemistry. His work laid the foundation for the modern understanding of chemical reactions, and his contributions to quantitative chemistry remain influential. He is also remembered for his tragic end, which has made him a symbol of the dangers of political upheaval and the importance of scientific freedom. Lavoisier's legacy in chemistry continued to have a profound impact long after his death. His law of conservation of mass and his discovery of the role of oxygen in combustion and respiration were fundamental to the development of the field of modern chemistry. His emphasis on quantitative analysis and measurement was also important in establishing chemistry as a science that could be studied in a systematic and rigorous manner. In addition to his scientific work, Lavoisier was also known for his contributions to the field of economics. He was a member of the Royal Commission on Agriculture and contributed to the development of the metric system of weights and measures. He also played a role in the establishment of the French stock exchange and served as a member of the Paris Chamber of Commerce. Despite his many accomplishments, Lavoisier's reputation suffered in the years following his execution. He was widely criticized for his association with the royal court and his involvement in taxation. However, his contributions to the development of modern chemistry were eventually recognized, and he is now regarded as one of the most important figures in the history of science. Today, Lavoisier is remembered in various ways. He has been commemorated on postage stamps, coins, and banknotes, and several scientific organizations have been named in his honor. His laboratory, which was located in the Louvre Palace, has been restored and is now a museum dedicated to his life and work. Lavoisier's work also had an impact beyond the field of chemistry. His ideas on the importance of measurement and quantification influenced the development of other sciences, including physics and biology. He was also an advocate for the use of scientific principles in industry and agriculture, which helped to increase productivity and efficiency. Lavoisier's collaboration with his wife Marianne Pauls was also significant. She was not only his wife but also his laboratory assistant and collaborator. She played an important role in his scientific work, including translating scientific papers from English and serving as an illustrator for his publications. In addition to his scientific and economic work, Lavoisier was also involved in public service. He was a member of the French Academy of Sciences and served on several committees, including the committee responsible for the reform of the French educational system. He also served as a commissioner for the Royal Gunpowder Administration, where he made significant contributions to the development of gunpowder manufacturing. Despite his many accomplishments, Lavoisier's life was cut short by his involvement in politics. During the French Revolution, he was accused of being a traitor to the revolution and was sentenced to death by the Revolutionary Tribunal. His execution was a tragedy not only for his family but also for the scientific community. One of Lavoisier's most significant contributions to the field of chemistry was his establishment of a new system of chemical nomenclature. At the time, the naming of chemical compounds was chaotic, with different substances having multiple names, which often varied depending on the region or language. Lavoisier's system was based on the principle of using names that reflected the composition of the compound, and his method became widely adopted throughout Europe and eventually worldwide. This system is still used in modern chemistry, with some modifications and updates, making Lavoisier the father of modern chemical nomenclature. Lavoisier's work also contributed to the development of atomic theory. He proposed that elements were composed of small, indivisible particles that he called atoms. Although his ideas about atoms were not fully developed, they set the stage for later work on atomic theory by other scientists such as John Dalton. Another significant contribution was his role in debunking the phlogiston theory, which was a widely held theory at the time that attempted to explain combustion. The phlogiston theory suggested that substances contained a substance called phlogiston, which was released during combustion. Lavoisier's work on combustion showed that oxygen was necessary for combustion to occur, and that substances actually gained weight during combustion, not lost it.
Ahmed Zewail was an Egyptian-American chemist and physicist who was born on February 26, 1946, in Damanhur, Egypt. He was one of the most prominent scientists of his time, and he is best known for his pioneering work in femtochemistry, which involves the study of chemical reactions at the femtosecond timescale, 1/4,000,000th of a second. Zewail grew up in Egypt and received his undergraduate degree in chemistry from Alexandria University in 1967. He then moved to the United States to pursue graduate studies at the University of Pennsylvania, where he earned a Ph.D. in chemical physics in 1974. After completing his doctoral studies, Zewail joined the faculty at the California Institute of Technology, Caltech, where he remained for the rest of his career. At Caltech, Zewail established the Femtosecond Dynamics Laboratory, which became one of the world's leading centers for the study of ultra-fast chemical reactions. He developed a technique called femtosecond spectroscopy, which allowed scientists to observe the behavior of molecules in real time at the femtosecond timescale. This breakthrough allowed researchers to gain a much deeper understanding of the mechanisms of chemical reactions. And it has had important implications for fields ranging from materials science to drug discovery. Zewail received many awards and honors for his work in femtochemistry, including the Nobel Prize in Chemistry in 1999. He was the first Egyptian to win a Nobel Prize in any field, and he was only the third Arab to win a Nobel Prize in any field. In addition to the Nobel Prize, Zewail received numerous other prestigious awards, including the National Medal of Science in 1997, the Priestley Medal in 2011, and the Order of Merit from the Egyptian government in 2009. Throughout his career, Zewail was also a strong advocate for science education and outreach. He founded the Zewail City of Science and Technology in Egypt, which is a research center and science museum that aims to inspire the next generation of Egyptian scientists. He also served as a science advisor to the United Nations and to the governments of Egypt and the United States. Sadly, Ahmed Zewail passed away on August 2, 2016, at the age of 70. He left behind a legacy of groundbreaking research and a commitment to using science to improve the world. Zewail's contributions to the field of femtochemistry were significant in understanding the mechanism of chemical reactions, which play a crucial role in a variety of areas such as environmental sciences, material science, and drug discovery. He and his research group were able to observe, manipulate and control the movements of atoms and molecules during chemical reactions using ultrafast laser techniques. In addition to his research, Swale was also a respected educator, mentor, and advocate for scientific literacy. He taught courses in chemical physics and physical chemistry at Caltech and supervised numerous graduate students and postdoctoral researchers in his lab. Many of his former students and colleagues have gone on to become leading scientists in their own right. In recognition of his contributions to science, Swale was elected to numerous scientific societies, including the National Academy of Sciences, the American Academy of Arts and Sciences, and the Royal Society of London. He was also a member of the Pontifical Academy of Sciences and the Academy of Sciences for the Developing World. In addition to his scientific work, Swale was an advocate for scientific collaboration and diplomacy. He believed that science could be a powerful tool for fostering understanding and cooperation among nations, and he worked tirelessly to promote international scientific partnerships. He was a member of several high-level international scientific committees and was frequently called upon to advise world leaders on issues related to science and technology. Swale's legacy continues to inspire scientists around the world to push the boundaries of scientific knowledge and to use their skills to improve the world. His commitment to education, mentorship, and international collaboration has had a profound impact on the scientific community and on society as a whole. After winning the Nobel Prize in 1999, Swale continued to receive numerous awards and recognitions for his groundbreaking research and contributions to science. In 2008, he was awarded the Othmer Gold Medal, the highest honor bestowed by the Chemical Heritage Foundation. He was also awarded the Benjamin Franklin Medal in Chemistry in 2011, one of the most prestigious science awards in the United States. Throughout his career, Swale was deeply committed to science education and outreach. He believed that science could be a powerful force for social and economic development, particularly in developing countries. In 2011, he founded the Swale City of Science and Technology in Cairo, Egypt, a state-of-the-art research center and science museum that aims to inspire and educate young people in the sciences. In addition to his research and advocacy work, Swale was also a prolific writer and speaker. He authored numerous scientific papers and several books, including Voyage Through Time, Walks of Life to the Nobel Prize and The Birth of Femtochemistry. He gave lectures and presentations around the world on topics ranging from science education to global development. Swale's legacy continues to inspire and influence scientists and policymakers around the world. His groundbreaking research in femtochemistry opened up new avenues of scientific inquiry and has led to important advances in a wide range of fields. His commitment to education and outreach has helped to inspire and train a new generation of scientists, particularly in the developing world. And his advocacy for international collaboration and diplomacy has helped to foster greater understanding and cooperation among nations, making the world a better and more peaceful place. In addition to his many scientific achievements, Swale was also a tireless advocate for diversity and inclusion in the sciences. He believed that science should be open to all, regardless of their background, and he worked to promote greater participation by women and underrepresented minorities in the sciences. Swale was also deeply committed to fostering international collaboration and diplomacy through science. He believed that scientific exchange and cooperation could help to build bridges between nations and promote understanding and peace. He served as a science advisor to the United Nations and was a strong supporter of international scientific partnerships, particularly in the developing world. Swale was widely recognized for his contributions to science and society, receiving numerous awards and honors throughout his career. In addition to the Nobel Prize, he was awarded the National Medal of Science, the Priestley Medal, the Franklin Medal, and the Order of Merit from the Egyptian government, among many others. Despite his many accomplishments, Swale remained humble and committed to using his scientific expertise to benefit humanity. He once said, "Science is not just a tool for advancing knowledge, it is a means of transforming the world." Through his groundbreaking research, his tireless advocacy for science education and international collaboration, and his unwavering commitment to social and economic development, Ahmed Swale left an indelible mark on the world of science and on the world as a whole. In conclusion, Ahmed Swale was a brilliant chemist, a dedicated educator, and a passionate advocate for science and international cooperation. His pioneering work in femtochemistry revolutionized our understanding of chemical reactions and paved the way for new discoveries and innovations. Dmitry Mendeleev was a Russian chemist and inventor who is best known for his creation of the periodic table of elements. Born in Siberia in 1834, Mendeleev's early life was marked by poverty and hardship. His father died when he was young, and he was forced to work odd jobs to support his family. Despite these challenges, Mendeleev was a brilliant student, and he excelled in mathematics and science. After studying at the University of St. Petersburg, he became a professor of chemistry at the University of Heidelberg in Germany, where he conducted research on the properties of gases and developed his early ideas about the periodic table. In 1869, Mendeleev published his landmark paper, The Relationship of the Properties of the Elements to Their Atomic Weights, in which he proposed the idea of the periodic table. His table arranged the elements in order of increasing atomic weight and grouped them based on their chemical and physical properties. This system allowed scientists to predict the properties of unknown elements based on their position in the table, and it helped to revolutionize the field of chemistry. Mendeleev's periodic table was not immediately accepted, and it was met with some skepticism from his colleagues. However, over time, his ideas were gradually adopted by the scientific community, and his table became the basis for the modern periodic table that we use today. In addition to his work on the periodic table, Mendeleev made numerous other contributions to the field of chemistry. He discovered new elements and compounds, and he developed important theories about chemical reactions and the behavior of gases. Mendeleev was also a gifted inventor, and he developed several practical applications for his scientific discoveries. He invented a new type of oil lamp, as well as a machine for measuring the density of gases. Throughout his career, Mendeleev remained committed to education and scientific outreach. He wrote several popular science books, including The Principles of Chemistry and The New View of the Universe, which helped to make science accessible to a wider audience. He also served as a mentor to many young scientists and played a key role in establishing the first chemical society in Russia. Mendeleev's contributions to science were widely recognized and celebrated during his lifetime. He was awarded numerous honors and awards, including the Davy Medal from the Royal Society of London and the Copley Medal from the British Academy of Sciences. In 1905, he was elected to the Russian Academy of Sciences. Dmitry Mendeleev died in 1907 at the age of 72. His contributions to the field of chemistry have had a profound impact on science and technology. And his periodic table remains one of the most important and enduring achievements in the history of science. In addition to his scientific work, Mendeleev was also involved in politics and social reform. He advocated for education reform and was a strong supporter of women's education, which was a relatively progressive stance for his time. He also served as a member of the Russian parliament and was a vocal advocate for democratic reforms. Mendeleev's legacy continues to inspire and influence scientists and educators around the world. His periodic table has become an iconic symbol of science and remains a fundamental tool for researchers and students alike. In recognition of his many contributions to science and society, the element with atomic number 101 was named Mendeleevium in his honor. Overall, Dmitry Mendeleev was a visionary scientist and inventor whose work has had a lasting impact on our understanding of the natural world. His contributions to chemistry and education have helped to shape modern science, and his legacy serves as an inspiration to future generations of scientists and innovators. Mendeleev's life and work have been extensively studied and analyzed by historians, scientists, and scholars. One area of particular interest has been his creative process in developing the periodic table. Mendeleev's approach to scientific inquiry was highly intuitive, and he relied heavily on his imagination and intuition in developing his theories. One of the most famous stories about Mendeleev's creative process involves his discovery of the periodic table. Legend has it that he was playing a game of solitaire and arranged the cards in rows and columns based on their suit and number. This arrangement inspired him to create a similar table for the elements, which he arranged based on their atomic weight and chemical properties. While the story may be apocryphal, it reflects Mendeleev's creative approach to scientific discovery. He was a firm believer in the power of intuition and imagination, and he saw science as a way of exploring the mysteries of the universe and unlocking its secrets. Mendeleev's legacy continues to be celebrated today, both in Russia and around the world. In Russia, he is considered one of the country's greatest scientists and is widely revered for his contributions to science and society. In 2007, the Russian government declared the year Mendeleev Year in honor of the 100th anniversary of his death, and numerous events and exhibitions were held throughout the country to celebrate his life and work. Overall, Dmitry Mendeleev was a pioneering scientist and inventor whose work has had a profound impact on our understanding of the natural world. His creativity, intuition, and passion for science continue to inspire and influence scientists and educators around the world, and his legacy serves as a testament to the power of imagination and discovery. Mendeleev's contributions to science went beyond the periodic table. He also made significant contributions to other areas of chemistry, including the study of solutions, the development of the concept of chemical valence, and the discovery of the critical temperature for gases. In the 1870s, Mendeleev turned his attention to the study of solutions and developed a theory to explain the behavior of solutions of different concentrations. His work on solutions helped to lay the foundation for modern physical chemistry and is still widely studied and applied today. Mendeleev's work on valence, or the combining capacity of atoms, was another important contribution to chemistry. He developed a system of notation for representing the valence of elements, which helped to clarify the relationships between different elements and their chemical properties. Mendeleev also made significant contributions to the study of gases. In 1869, he discovered the critical temperature for gases, which is the temperature above which a gas cannot be liquefied, regardless of the pressure applied. This discovery helped to lay the foundation for the field of physical chemistry and has important implications for industrial processes such as the production of liquefied gases. Mendeleev's scientific contributions were recognized and honored throughout his lifetime. He received numerous awards and honors, including the Davy Medal from the Royal Society in 1882, and was elected a foreign member of the Royal Society in 1892. He was also awarded the Order of St. 1. Rusting of iron. When iron reacts with oxygen and water, it forms iron 3 oxide, which is commonly known as rust. The chemical equation for this reaction is 4Fe plus 3O2 plus 6H2O 4FeO3. 2. Combustion of iron. When iron is heated in the presence of oxygen, it reacts to form iron 3 oxide. The chemical equation for this reaction is 4Fe plus 3O2 2Fe2O3. 3. Reaction of iron with chlorine gas. When iron is heated in the presence of chlorine gas, it reacts to form iron 3 chloride. The chemical equation for this reaction is 2Fe plus 3Cl2 2Fe3. 4. Reaction of iron with sulfur. When iron is heated in the presence of sulfur, it reacts to form iron 2 sulfide. The chemical equation for this reaction is Fe plus S-Fes. 5. Reaction of iron with carbon monoxide. When iron is heated in the presence of carbon monoxide, it reacts to form iron carbonyl. The chemical equation for this reaction is Fe plus 5 Co-Fe Co5. 6. Reaction of iron with nitric acid. When iron reacts with nitric acid, it forms iron 3 nitrate and nitrogen dioxide gas. The chemical equation for this reaction is 2Fe plus 6 No3 2Fe No3 3 plus 3H2O plus 2 No2. 7. Reaction of iron with hydrochloric acid. When iron reacts with hydrochloric acid, it forms iron 2 chloride and hydrogen gas. The chemical equation for this reaction is Fe plus 2 HCl 2 plus H2. 8. Reaction of iron with sulfuric acid. When iron reacts with sulfuric acid, it forms iron 2 sulfate, hydrogen gas, and water. The chemical equation for this reaction is Fe plus H2SO4 FeSO4 plus H2 plus H2O. 9. Reaction of iron with copper sulfate. When iron reacts with copper sulfate, it forms iron 2, sulfate and copper. The chemical equation for this reaction is Fe plus QSO4 FeSO4 plus 2. 10. Reaction of iron with sodium hydroxide. When iron reacts with sodium hydroxide, it forms iron 2, hydroxide and hydrogen gas. The chemical equation for this reaction is Fe plus 2 no Fe O2 plus H2. 11. Reaction of iron with potassium permanganate. When iron reacts with potassium permanganate, it forms iron 3, oxide and manganese 2, oxide. The chemical equation for this reaction is 4 Fe plus 3 CMO 4 4 Fe O3 plus 3 MO 2 plus 3 Co. 12. Reaction of iron with hydrogen peroxide. When iron reacts with hydrogen peroxide, it forms iron 3, oxide and water. The chemical equation for this reaction is 2 Fe plus 3 H2O 2 Fe 2 O3 plus 3 H2O. 13. Reaction of iron with aluminum. When iron reacts with aluminum, it forms iron 3, oxide and aluminum oxide. The chemical equation for this reaction is 4 Fe plus 3 Al 2 Fe 2 O3 plus 3 Al 2 O3. 14. Reaction of iron with potassium dichromate. When iron reacts with potassium dichromate, it forms iron 3, oxide and chromium 3, oxide. The chemical equation for this reaction is 4 Fe plus 3 K2Cr2O7 plus 7 H2SO4 4 FeSO4 plus 3 Cr2SO4 3 plus K2SO4 plus 7 H2O. 15. Reaction of iron with sulfur dioxide. When iron reacts with sulfur dioxide, it forms iron 2, sulfite and sulfur. The chemical equation for this reaction is Fe plus SO2 FeSO3 plus S. 16. Reaction of iron with ammonium chloride. When iron reacts with ammonium chloride, it forms iron 2, chloride, ammonia, and hydrogen gas. The chemical equation for this reaction is Fe plus 2 NH4Cl Fcl 2 plus 2 NH3 plus H2. 17. Reaction of iron with sodium chloride. When iron reacts with sodium chloride, it forms iron 3, chloride and sodium. The chemical equation for this reaction is 2 Fe plus 6 NaCl 2 Fcl 3 plus 6 Na. 18. Reaction of iron with sodium bicarbonate. When iron reacts with sodium bicarbonate, it forms iron 3, oxide, sodium carbonate, water, and carbon dioxide gas. The chemical equation for this reaction is 4 Fe plus 3 NaCO 3 2 Fe 2O3 plus 3 Na 2 Co 3 plus 3 H2O plus 3 Co 2. 19. Reaction of iron with sodium carbonate. When iron reacts with sodium carbonate, it forms iron 3, oxide, sodium oxide, and carbon dioxide gas. The chemical equation for this reaction is 4 Fe plus 3 Na 2 Co 3 2 Fe 2 O3 plus 3 Na 2 O plus 3 Co 2. 20. Reaction of iron with potassium hydroxide. When iron reacts with potassium hydroxide, it forms iron 2, hydroxide and potassium. The chemical equation for this reaction is Fe plus 2 Co Fe O2 plus 2K. 21. Reaction of iron with hydrochloric acid. When iron reacts with hydrochloric acid, it forms iron 2, chloride and hydrogen gas. The chemical equation for this reaction is Fe plus 2 HCl Fcl 2 plus H2. 22. Reaction of iron with nitric acid. When iron reacts with nitric acid, it forms iron 3, nitrate, nitrogen dioxide gas, and water. The chemical equation for this reaction is 2 Fe plus 6 No 3 2 Fe No 3 3 plus 3 No 2 plus 3 H2O. 23. Reaction of iron with acetic acid. When iron reacts with acetic acid, it forms iron 3, acetate, hydrogen gas, and water. The chemical equation for this reaction is 2Fe plus 6CH3 Cu 2Fe Che Cu 3 plus 3H2. 24. Reaction of iron with sulfuric acid and hydrogen peroxide. When iron reacts with sulfuric acid and hydrogen peroxide, it forms iron 3, sulfate, water, and oxygen gas. The chemical equation for this reaction is Fe plus H2SO4 plus H2O2 Fe 2SO4 3 plus 2 H2O plus O2. 25. Reaction of iron with chlorine gas. When iron reacts with chlorine gas, it forms iron 3, chloride. The chemical equation for this reaction is 2Fe plus 3Cl2 2Fecal 3. 26. Reaction of iron with copper 2, sulfate. When iron reacts with copper 2, sulfate, it forms iron 2, sulfate and copper metal. The chemical equation for this reaction is Fe plus QSO4 FeSO4 plus 2. 27. Reaction of iron with lead 2, nitrate. When iron reacts with lead 2, nitrate, it forms iron 2, nitrate and lead metal. The chemical equation for this reaction is Fe plus Pb NO3 2 Fe NO3 2 plus Pb. 28. Reaction of iron with silver nitrate. When iron reacts with silver nitrate, it forms iron 2, nitrate and silver metal. The chemical equation for this reaction is Fe plus 2 Ag NO3 Fe NO3 2 plus 2 Ag. 29. Reaction of iron with sodium hydroxide. When iron reacts with sodium hydroxide, it forms iron 2, hydroxide and hydrogen gas. The chemical equation for this reaction is Fe plus 2 No Fe O2 plus H2. 30. Reaction of iron with zinc chloride. When iron reacts with zinc chloride, it forms iron 2, chloride and zinc metal. The chemical equation for this reaction is Fe plus ZnCl2 Fecal 2 plus Cn. These are just a few examples of the many reactions that iron can undergo. Each reaction has its own unique set of conditions and products. And understanding these reactions is crucial for a deeper understanding of chemistry and the natural world. These reactions demonstrate the versatility of iron and its ability to form a wide range of compounds with various elements and compounds. Understanding these reactions is key to understanding the behavior of iron in various environments and applications, from industrial processes to biological systems. A chemical element is a substance that cannot be broken down further into simpler substances by chemical means. Each element is characterized by a unique set of properties, such as atomic number, atomic weight, and electron configuration. The theory of chemical elements is based on the idea that all matter is composed of atoms, and that each atom is made up of a nucleus, which contains protons and neutrons, and electrons, which orbit the nucleus. The number of protons in an atom's nucleus determines its atomic number, which in turn determines the element to which it belongs. There are currently 118 known elements, which are arranged in the periodic table according to their atomic structure and chemical properties. The periodic table is a powerful tool for predicting the chemical behavior of elements and their compounds, and is an essential tool for understanding chemistry and the natural world. The properties of elements can be explained through various theories and models. One such model is the Bohr model, which explains the arrangement of electrons in an atom's energy levels. The modern quantum mechanical model explains the behavior of electrons as a wave-like function, providing a more accurate and complex understanding of an atom's electron configuration. Elements can also be classified based on their chemical and physical properties. Metals, nonmetals, and metalloids are examples of such classifications. Metals are generally good conductors of heat and electricity, have a high melting and boiling point, and are malleable and ductile. Nonmetals, on the other hand, are poor conductors of heat and electricity, are typically brittle and have low melting and boiling points. Metalloids have properties of both metals and nonmetals. The study of elements and their interactions with each other is known as chemistry. Chemistry helps us to understand the world around us, and has a wide range of applications in fields such as medicine, materials science, and environmental science. Elements can also combine with each other to form compounds, which are molecules made up of two or more different elements. The properties of compounds are different from those of their constituent elements. For example, sodium and chlorine are both highly reactive elements, but when they combine to form sodium chloride, table salt, the compound is relatively stable and non-reactive. Chemical reactions involve the transformation of one or more substances into different substances through the breaking and forming of chemical bonds. The study of chemical reactions is an important part of chemistry and helps us understand the behavior of matter in our environment. In summary, chemical elements are the basic building blocks of matter, and their properties and behavior can be explained through various theories and models. Understanding the properties of elements and their interactions with each other is fundamental to the study of chemistry, and has a wide range of applications in many fields of science and technology. The discovery of new elements and the development of new techniques for studying their properties is an ongoing area of research in chemistry. Scientists continue to explore the properties and behavior of elements and their compounds, as well as their applications in various fields. One example of this is the development of new materials for use in various industries. For instance, the discovery of new rare earth elements and their compounds has led to the development of advanced magnets used in electric motors and wind turbines. Similarly, the discovery of new elements and their compounds has also led to the development of new catalysts for use in the production of pharmaceuticals, plastics, and other materials. Another important area of research is the study of the environmental impact of chemical elements and their compounds. Many elements, such as lead and mercury, are toxic to humans and the environment, and their use in industry and consumer products has been regulated or banned in many countries. Understanding the behavior and impact of elements in the environment is essential for mitigating their negative effects and promoting sustainable development. One important concept in the study of chemical elements is their isotopes. Isotopes are atoms of the same element that have the same number of protons, but a different number of neutrons. This results in isotopes having a different atomic mass. Isotopes of an element have similar chemical properties, but may have different physical properties, such as their stability and radioactive decay. Radioactive isotopes, in particular, have important applications in fields such as medicine, energy production, and environmental science. For example, radioactive isotopes can be used in medical imaging to diagnose and treat diseases. In nuclear reactors to produce energy, and in environmental science to study the movement and behavior of pollutants. The properties of elements can also be affected by the conditions in which they are found. For example, some elements may have different allotropes, which are different forms of the same element that have different structures and properties. For instance, carbon can exist in different allotropes, such as diamond, graphite, and fullerenes, each with unique properties and applications. In addition, Elements can exist in different states of matter, such as solid, liquid, and gas, depending on their temperature and pressure. Understanding the behavior of elements in different states of matter is important for many applications, such as materials science and the study of atmospheric and geological processes. The periodic table is a fundamental tool for organizing and understanding the properties and behavior of chemical elements. It is a table that arranges elements in order of increasing atomic number and organizes them into rows and columns based on their electronic structure and chemical properties. The periodic table allows scientists to predict the properties of unknown elements and compounds and to understand the relationships between different elements. The periodic table is divided into groups or families, which are columns of elements with similar chemical and physical properties. For example, the alkali metals, such as sodium and potassium, are highly reactive and have similar properties, such as low melting points and good electrical conductivity. Similarly, the noble gases, such as helium and neon, are inert and have low reactivity and high stability. The periodic table also includes periods, which are rows of elements that follow a repeating pattern of properties. The electron configuration of elements determines their position in the periodic table and their properties. For instance, elements in the same group have the same number of valence electrons, which are responsible for their chemical behavior. In addition to organizing known elements, the periodic table is also used to predict the properties of unknown elements. For example, the discovery of gaps in the periodic table led to the prediction and subsequent discovery of new elements, such as gallium and germanium. In conclusion, the periodic table is a crucial tool for organizing and understanding the properties and behavior of chemical elements. It allows scientists to predict the properties of unknown elements and compounds, and has led to the discovery of new elements and compounds. The periodic table is a foundational concept in chemistry and is used extensively in research and industry. The study of chemical elements is a diverse and important area of science with many applications in various fields. The properties and behavior of elements can be affected by various factors, such as their isotopes. Alkenes are hydrocarbons that contain a carbon-carbon double bond. The general formula for alkenes is CnH2n, where n is the number of carbon atoms. Alkenes are unsaturated hydrocarbons, meaning they can undergo addition reactions to form saturated compounds. Nomenclature: the IUPAC system is used for the nomenclature of alkenes. The parent chain should contain the double bond, and the position of the double bond is indicated by the lowest numbered carbon atoms that it is attached to. The suffix -ene is added to the name of the parent chain to indicate that it is an alkene. For example, ethene is the simplest alkene and is also called ethylene, while propene is the alkene with 3 carbon atoms and is also called propylene. Characteristic reactions. 1. Addition reactions. Alkenes can undergo addition reactions with electrophilic reagents such as hydrogen halides, water, and hydrogen. For example, in the addition of hydrogen halides, the hydrogen atom is added to one carbon atom of the double bond, and the halogen is added to the other carbon atom. 2. Oxidation reactions. Alkenes can be oxidized by strong oxidizing agents such as potassium permanganate and ozone to form diols or ketones. 3. Polymerization reactions. Alkenes can undergo polymerization reactions to form long-chain polymers. The most common example is the polymerization of ethene to form polyethylene. 4. Isomerization reactions. Alkenes can undergo isomerization reactions to form different isomers. For example, in the isomerization of 1-butene, the double bond is shifted from the first to the second carbon atom. 5. Elimination reactions. Alkenes can also undergo elimination reactions where a molecule of water, hydrogen halide, or other small molecule is removed to form a double bond. This reaction is often used in organic synthesis to form alkenes from alkyl halides, alcohols, or ethers. 6. Hydration reactions. Alkenes can undergo hydration reactions in which water is added to the double bond, forming an alcohol. This reaction is often catalyzed by strong acids such as sulfuric acid or phosphoric acid. 7. Halogenation reactions. Alkenes can undergo halogenation reactions with halogens such as chlorine and bromine. In these reactions, the halogen is added to one carbon of the double bond, and the other carbon becomes positively charged. 8. Hydroboration oxidation reactions. Alkenes can undergo hydroboration oxidation reactions in which borane is added to the double bond, forming an alkylboron. This intermediate is then oxidized with hydrogen peroxide or another oxidizing agent to form an alcohol. 9. Diels-Alder reactions. Alkenes can undergo Diels-Alder reactions, which are a type of cycloaddition reaction that involves the formation of a new cyclic compound. In this reaction, a diene, a molecule with two double bonds, reacts with a dienophile, a molecule with a double bond, to form a cyclohexene ring. 10. Reduction reactions. Alkenes can undergo reduction reactions in which the double bond is converted into a single bond by adding hydrogen or another reducing agent. This reaction is commonly used to synthesize alkanes from alkenes. 11. Ozonolysis reactions. Alkenes can undergo ozonolysis reactions, which involve the cleavage of the double bond and the formation of two carbonyl compounds. In this reaction, ozone is used to break the double bond, and the resulting ozonide intermediate is then treated with a reducing agent such as zinc or dimethyl sulfide to form the carbonyl compounds. 12. Cycloaddition reactions. Alkenes can undergo cycloaddition reactions, which involve the formation of a cyclic compound from two or more molecules. One example is the 2+2 cycloaddition reaction, in which two alkenes react to form a cyclobutane ring. 13. Wittig reactions. Alkenes can also undergo Wittig reactions, which involve the conversion of a carbonyl compound into an alkene. In this reaction, a phosphorus ylide is used to transfer an alkyl or aryl group to the carbonyl carbon, forming an alkene. 14. Enzymatic reactions. Alkenes are also involved in many biological processes and can undergo enzymatic reactions. One example is the biosynthesis of fatty acids, in which acetyl-CoA is converted into malonyl-CoA, which then undergoes a series of reactions to form long-chain fatty acids containing multiple double bonds. 15. Polymerization reactions. Alkenes can undergo polymerization reactions, in which monomers are linked together to form a polymer. This reaction is commonly used to produce synthetic materials such as plastics and rubber. One example is the polymerization of ethylene to form polyethylene, a widely used plastic. 16. Isomerization reactions. Alkenes can also undergo isomerization reactions, in which the position of the double bond is changed. This reaction can be catalyzed by heat, acids, or other catalysts, and is often used in the synthesis of complex organic molecules. 17. Grignard reactions. Alkenes can undergo Grignard reactions, which involve the addition of a Grignard reagent, an organometallic compound, to the double bond. This reaction can be used to synthesize a wide range of organic compounds, including alcohols, ketones, and carboxylic acids. 18. Ozonide reactions. Alkenes can undergo ozonide reactions, in which an ozonide intermediate is formed and then treated with a reducing agent to form two carbonyl compounds. This reaction is often used to identify the position of a double bond in an unknown compound. 19. Esterification reactions. Alkenes can undergo esterification reactions, in which an alcohol and a carboxylic acid react to form an ester. This reaction is commonly used in the synthesis of fragrances and flavors. 20. Wittig-Horner reactions. Alkenes can undergo Wittig-Horner reactions, which involve the conversion of a carbonyl compound into an alkene using a phosphorus ylide and an ester. This reaction is often used in the synthesis of complex organic molecules. 21. Alkene metathesis reactions. Alkenes can undergo alkene metathesis reactions, which involve the exchange of alkene groups between two molecules. This reaction is catalyzed by metal catalysts such as ruthenium and is often used in the synthesis of complex organic molecules and polymers. 22. Hydrogenation reactions. Alkenes can undergo hydrogenation reactions, in which the double bond is converted into a single bond by adding hydrogen gas and a metal catalyst such as platinum or palladium. This reaction is commonly used to convert unsaturated fats into saturated fats for food processing. 23. Halohydrin reactions. Alkenes can undergo halohydrin reactions, in which a halogen and a hydroxyl group are added to opposite sides of the double bond. This reaction is often used in the synthesis of pharmaceuticals and agrochemicals. 24. Diazonium coupling reactions. Alkenes can undergo diazonium coupling reactions, in which a diazonium salt is coupled with an alkene to form an azo compound. This reaction is commonly used in the synthesis of dyes and pigments. 25. Hydroformylation reactions. Alkenes can undergo hydroformylation reactions, in which a carbonyl group is added to the double bond using carbon monoxide and a metal catalyst such as rhodium. This reaction is often used in the synthesis of aldehydes and higher alcohols. 26. Enzymatic epoxidation reactions. Alkenes can undergo enzymatic epoxidation reactions, in which an enzyme such as cytochrome P450 is used to add an epoxide group to the double bond. This reaction is important in the metabolism of drugs and other xenobiotics. 27. Acylation reactions. Alkenes can undergo acylation reactions, in which an acyl group is added to the double bond using an acid anhydride or acid chloride. This reaction is commonly used in the synthesis of esters and amides. 28. Radical reactions. Alkenes can undergo radical reactions, in which a radical species such as a halogen or a peroxide is used to initiate a chain reaction.